All right, so we've been talking a lot about how alkynes react, but what if we wanted to actually make alkynes? So instead of doing the opposite of an addition reaction, is actually, of course, an elimination reaction. So what are ways to actually make alkynes, right? So we're going to need to make an alkyne, because there's 2 pi bonds, we need to do 2 eliminations. We're going to need really strong bases to do this. So things like NaNH2, which of course is an ionic bond. So it's really like this. Nitrogen with a negative charge. Butyl lithium, which is carbon with a negative charge, bonded to a lithium, right, an ionic bond. And really anything else, right, with a nitrogen bonded to a lithium, that would of course be a negative and a plus there. Right? Things with carbon with a negative charge or nitrogen with a negative charge are really strong bases. They're going to help us do these eliminations. So to do these eliminations, we're going to need to do 2 eliminations, which means of course we're going to need 2 leaving groups, right? In either case, and a really, really strong base. So the key here is to form those 2 pi bonds. We need 2 leaving groups, so they could be on 2 different carbons next to each other or on the same carbon. And we're really going to need that strong base, so a nitrogen or carbon with a negative charge. So what is this going to look like in reality? So it's going to happen. These are essentially E2 reactions, 2 E2 reactions. So all the rules apply for E2 as before. Things need to be anti-periplanar, right? Anti-periplanar. So it's all in one step. So we take our strong base. It's going to grab the hydrogen, which of course is lined up 180 degrees away from our bromine. We're going to form that pi bond, at the same time break the carbon-bromine bond. That makes our first pi bond. Now again, we look for that beta hydrogen. You notice in this case, the bromines are on 2 different carbons. We look for that beta hydrogen. The base comes in again, reacts. Look at the bromine, it has to be anti to the hydrogen. Right? We get that anti-periplanar. The bromine comes in, reacts, forms another pi bond, and the leaving group leaves. That Z isomer, that anti-coplanar, takes place. They talk about some of this down here, but with actually taking place, but I don't believe really that's of importance to us. I would really focus on things need to be anti-periplanar for this E2 to take place. So here I have an example of a mechanism for using the halogens on the same carbon. So I'm using N-butyllithium, a really strong base. I already have it set up that this hydrogen, the beta hydrogen, alpha beta hydrogen, 2 bonds away, is already anti-periplanar to this bromine. Using strong base, butyl lithium, carbon with a negative charge, takes the hydrogen, forms a pi bond, kicks out the bromine. What does that result in? All right, so that results in this alkyne. Now, if we want this to keep reacting, we're going to need a second equivalent. So this is one equivalent. We're going to need a second equivalent of butyl lithium, a really strong base. The first time we made butane, right? So this was short of hydrogen. Now it has 3 hydrogens there. We need a lithium bromine salt, bromine, balance our charges. So let's add another N-butyl lithium, negative charge there. Of course, it has 2 hydrogens on it right now, but it's going to get that third one. Hydrogen and bromine are trans to each other, so we set that up nicely. So we can do this another E2 elimination. Take that out. What are we going to make now? We're going to make an alkyne. Of course, easy way to draw the alkyne. Let's draw the alkyne first. So that would be carbon 1. Alkyne was between carbon 2 and 3 now, and 4. We added a hydrogen to this now, so we made another molecule of butane. And we made another lithium bromide salt from the bromine leaving and the other lithium here. We get our alkyne. So this is a double E2 elimination to form alkynes. So either from the bromine on the same carbon, as shown here, or in the previous we talked about bromines being on 2 different carbons. But either way, double E2, anti-periplanar is the key. All right, the last part of synthesizing alkynes is we're going to take advantage of something we already actually know. And that is because of the hybridization state of alkynes being sp hybridized, those carbons, versus sp2 hybridized versus sp3. The distance from the nucleus is different, which means, right, when we have a negative charge, we have a lone pair in an sp orbital, that's closer to the nucleus. That makes it more stable, right? Versus sp2 or sp3 when they're farther away. So if you need to review the acid-base and hybridization video, I would do that. But what we're going to do here is we're going to take terminal alkynes. We're going to take those same kind of strong bases we looked at before, with those double eliminations. And what we're going to do is deprotonate, again, an acid-base reaction, to make a negatively charged carbon called an acetylide ion, which is a sp hybridized negative charge, so a lone paired and sp orbital. And that is going to be a great nucleophile. And we're going to be able to use this to make carbon-carbon bonds. So here we have an acetylide ion. Let's look at the mechanism for this. What's going to happen? It'll be a really strong base, nitrogen negative charge. What that's going to do is going to deprotonate the CH, and that's going to give us a carbanion on the alkyne, on carbon 1. Careful to number our carbons always. And then essentially this can react with any kind of electrophile we want to, right? So we can add carbon-carbon bonds now. So let's draw an electrophile. We're going to do like SN2 type reactions. We got to be careful. If we're going to do SN2 type reactions, we know we can't have anything that's a tertiary alkyl halide. We got to do primary or secondary alkyl halides. So you got to be careful what we pick. So this is a secondary alkyl halide. So we can do an SN2. So backside attack before. And what we've done is we've formed a new carbon-carbon bond. 1, 2, 3, 4. So I call this 5, 6, 7, 5, 6, 7. So the nucleophile was the carbon that we deprotonated in the first step. Negative charge carbon can do an SN2, so carbon 1 and carbon 6 are now bonded. Lose bromine. And we actually formed a new internal alkyne with this carbon-carbon bond formation. So it's another nice way to make CC bonds, or first way you know how to make CC bonds, and to make an internal alkyne. But it takes advantage of that stuff we learned before about acid-base chemistry based on hybridization state. So this is just showing this again. I already showed you one example was the NH2 minus, which is a really strong base of the nitrogen with a negative charge. That ends up making a carbon with a negative charge, that acetylide ion. Or you could also use N-butyl-lithium, which we saw before, carbon with a negative charge, right? This is an ionic bond, just like this is an ionic bond. They'll deprotonate the CH, so you have a carbon with a negative charge. We can essentially do SN2 reactions with R, X. So the main thing we need to remember, though, it must be a primary or secondary alkyl halide. It can't be tertiary because you can't do SN2s with tertiary. And we can make a new internal alkyne.